again, Beverly. This is a little brief lecture on how to make the calculations I've asked you to make in Mission Toothbrush. So on my screen here, or on my drawing, I've got a wire, okay? And for the purposes of this discussion, we're just gonna assume that there is current in the wire. Why there's current there, apparently a battery was hooked up to a motor or perhaps a toothbrush or something like that. What we're going to do is we're going to zoom in with sort of microscopic vision to see what's going on in the wire and what exactly that might mean. So first of all, I just want to say a couple of things about electrical current. So as you may know from our discussions about semiconductors or perhaps your study of chemistry, you may know that in the physical structure of the wire, the electrons are what are moving in order to carry the current. However, you could alternatively think about current as the movement of the absence of electrons in the other direction. These electron holes that we discussed in our PN junction unit were essentially what you could imagine what would happen if you thought about current as being positive but moving opposite the negative electrons. So conventional current is what we say when we're talking about the movement of current from the positive terminal of the battery to the negative terminal of the battery. And we're going to just assume conventional current throughout this entire course because that's essentially what engineers do. We assume that the current is flowing from plus to minus, even though we know that we could also think about that as electrons flowing from minus to plus. So in my sketch here, these blue dots are actually the electron holes moving in the direction from plus to minus, okay? You'll get used to that. I know it's a little confusing to think about at first. The reason for this is, you guessed it, historical. The history of physics and engineering was that scientists didn't know that the electron existed until about the year 1890 or 1895, but people had been developing an understanding of the flow of electric charge for 100 or 120 years before that. Initially, the first experiments with electricity were done in Renaissance Italy in the 1750s, 1780s. And also Benjamin Franklin came along in the early 1800s and started discussing these, positives and negatives and things. But the actual electron was not discovered until well after people had been thinking about circuits. So conventional current is based on the assumptions that we have historically that current flows from positive to negative. And that's what we're going to do here. But it's essentially, from a math point of view, going to get you exactly the same results. So we've got these quote unquote positive charges, these electron holes that are moving to the negative terminal in our battery. We're going to give that flow of charge a name. We're going to call it current, okay? And the unit for current in the metric system is amperes, okay? Amperes are named after Andre Ampere, okay? And it's also abbreviated amps, okay? And also abbreviated A for amps, okay? An ampere is what you get if you were an observer sort of watching, let's say that you were like, there's like a start line or something, or a finish line for a marathon, and you were an observer watching that line, and you were essentially counting the number of charged particles going past that line per unit time. That's really what current is, okay? So current, in the sort of most basic sense, is the flow of charge per unit time past some arbitrary reference point in a wire, okay? So I use the symbol I for current, Okay, the symbol we use for charge in physics and engineering is Q. Okay, time, you're not going to be surprised, is T. So current is the amount of, we use delta for sort of change in charge and delta for change in time. So current is that amount of charge per unit time past our area in the wire. The unit for charge is this thing called the coulomb, okay? Coulombs of charge, seconds for time. All right, so 1 ampere is what you would see if 1 coulomb of charge went past your location in the wire every second. Now, just so you know, an ampere actually is quite a large amount of current. And in terms of what could be physically challenging to you, like if you, for example, got electrocuted, you could get seriously hurt by much less than 1 ampere. But if you took about 70 milliamps straight to the heart, that could absolutely reset your heart. So current is the dangerous guy in electricity. Voltage, not so much. All right, so let's just summarize here. I've got my, I'm going to write my equation in symbols. I is equal to delta Q over delta T. I'm going to write my equation in sort of SI units, the metric system units. Amperes is coulombs per second. Okay. In abbreviation, that's amps is coulombs per second, like that, sorry. And then finally, I just wanted to talk to you a little bit about what a coulomb even means, okay? When in physics class or just in general life, you might remember that we say things like opposites attract and likes repel, okay? So like, let's say we've got a proton and an electron and those two things attract each other. Or for example, let's say that we've got an electron and those two things repel each other. The property of the matter that is making that repulsion or attraction or that force occur is the charge. Okay, so charge is a quality of some types of matter, many types of matter, and its SI unit is coulombs. Okay, so finally, let me just talk to you a little bit about the calculation I want you to make. So batteries will provide charge to devices. When current flows from a battery to a device, charge comes out of the battery, flows through the circuit. So, sorry, I ran out of paper. If your current is, let's say, 2 amps, okay, and let's say that you measured current out of the toothbrush at 2 amps for 3 seconds. The charge in that instance, the 2 amps over 3 seconds, is 6 coulombs, okay? Number one. Number two, the capacity of a battery is often referred to in terms of the charge stored in it. In other words, if you use up, or if the battery puts out this much charge over time, it will die. So if you look at the battery, or if you look up like the charge capacity of the battery, you will not see a number in coulombs. You will see a number that looks like that. Why? Why on earth would something like that be a label for charge? Well, let's think about it. If current is charge over time, charge is current times time. And if you have a reading of current accumulating over some amount of time, that is equivalent to an amount of charge. Okay, let me say that again. If you look up the capacity of a battery, right, like the ability for a battery to provide charge to a device and power it over time, you do not look up a number of coulombs, you look up a number of milliampere hours. Sometimes you'll, for bigger batteries like in cars, it'll say something like ampere hours. The idea would be that, for example, if you had a battery that had a capacity of 900 milliampere hours, what that means is that your battery can power a circuit if it were drawing 900 milliamps for 1 hour. Okay. On the other hand, if your battery, for example, were providing 100 milliamps to a circuit, it could power it for 9 hours or any combination thereof. Okay. If on an extreme end, let's say that you had a circuit where your battery was only providing 1 milliamp to a device, it could run it for 900 hours. Okay. So that's some insights into Mission Toothbrush. Good luck.